Hi, everyone. Welcome at our weekly TCS seminar at the Agilonian. Today we have a speaker from Hungary, Dömötör Pálvölgyi. I'm sorry for butchering your name, but you should be used to it. Dömötör works at Eötvös Loránd University in Budapest. Over last years, I saw lots of activity from Dömötör on hypergraph colorings and coverings, specifically in the geometric setup, like I don't know, point sets in the plane and disks being hyperedges, and yeah. So that's an exciting and very rich line of research. But I do know your results, Dömötör, from say kind of random other topics. I know very nice result in combinatorics of posets. I remember your one or two papers about slope number of graphs. So something really more into graph drawing, I think.
Yeah.
Oh,
yeah,
you
that's
don't remember.
I started.
Yeah.
No, I just couldn't catch the word slope. I heard it as slope. The slope number is interesting.
Yes, and today your the topic of your talk is actually something like two-sentence thing you can talk about. It's a bipartite graph, n vertices on one side and vertices on the other side, and you just count the number of stable matchings. And I understand that you improved drastically the upper bound. So we are very happy to have you here, and please start whenever you're ready.
Thank you. So for butchering my name, I try to take revenge. Drodzy słuchacze, mamy przyjemność zaprosić Państwa na wystąpienie Dömötöra Pálvölgyiego. It was just very nice to read the email that you sent around and to see my name conjugated in Polish as well.
That's what we do, we conjugate.
Yeah, that's good. Okay, now I'm sharing the screen, and I guess it's not full screen, right? And now it is full screen. Good. Amazing. Then let me move the windows around. So welcome everyone. Oops, don't go yet. As Piotr said, I talk about the number of stable matchings. I proved that there aren't too many of them. And all this is joint work with Corey Palmer from the University of Montana. Although we did start this project in Budapest quite some time ago, exactly like a couple of weeks before the COVID thing started. So slightly before 2 years ago, but then it took a long time to finish the details and to get the best bound that I will tell you today. Okay, so first let me give an outline of the talk. I start with an outline of the talk. After that, I mentioned that I usually don't like to talk about outlines, but this time I thought it would be necessary to tell the outline of the talk. And of course, I did it already the first time when I gave the talk. So now this is a repeat of this terrible joke. Then I go on with the outline of the talk and with the repeat of my terrible joke. And then I tell you a new method for counting, because the way that we achieved our upper bound, we developed a new method that is practically an entropy method, except that Corey and I are not smart enough to really know how entropy works, and we couldn't work with entropies. So if you wanted, then this is an easier method than entropy. Those of us who are not skilled enough in that can use this. Then to show you how to use it, first I prove Bregmann's theorem. Radhakrishnan had a nice proof with entropy. I rewrap it and say it with our language. And then I'll define stable matchings, rotations, and tangled grids. I'll tell you what these are. And then I tell you how we can use our method to count down sets in tangled grids, and somehow they will be in bijection with stable matching. So that's how we get our upper bound. And then at the end, I'll thank you for your attention. So this is the outline, but you know what? Forget it. I'd rather just start with stable matchings instead. So what's a stable matching? Let's suppose that you have a collection of men and women. Let's say on the left you have Kylo Ren, Finn, Poe, Chewbacca, and on the right you would have Rey, Rose, that the girl in the helmet whose name I forgot, and Maz. And you want to find a stable matching in this graph. So note it's important that it's a bipartite graph. This was introduced in the 70s, so no man and man matchings are allowed. In fact, nowadays people prefer to say this problem as matching jobs to applicants. A famous application is this hospital residency problem, or you can also think about when students want to go to college and you want to find a matching. Just because most people know it in this way, I'll present it in the form of stable matching or stable marriages. Okay, so what is the problem? We are given a complete bipartite graph among n men and n women, and we have a preference list. Let's say Kylo would prefer to be matched or married with Ray, then his second choice would be Rose, his third choice would be that girl in the helmet, and his last choice would be Maz. And another person, let's say Poe, might have a completely different ordering. Maybe he prefers that girl in the helmet and then Ray and so on. And the same goes for the women. They also have a preference list on the man, which is of course completely different from the man's preference list. There's no correlation needed. Let's say Rose, first choice would be Finn, and his last choice would be Kylo Ren. And then once you find a matching, you say that it's a stable matching if you don't have a blocking edge. What is a blocking edge? Let's say in this example, if this was the matching, then the edge between Finn and Ray would be a blocking match, because Finn's first choice would be Ray, and most likely Ray's first choice would be also Finn. So notice that this blocking edge, it doesn't matter what Kylo Ren's or Rose's or any other person's preference list is. This only depends on Finn's and Ray's preference list. If they prefer each other to their current partners, then that's a blocking edge. Then they would just, I don't know, get divorced and marry each other. Okay. So this was the definition of stable matchings. I'm sure that most of you are familiar with this notion. And the classic theorem that's 60 years old by Gale and Shapley says that stable matchings always exists. So as I said earlier, this has many applications. In fact, they even received the Nobel Prize for it. It's that important. And Knut asks not much later, he has that how many different ways can we have to have stable matchings among n men and n women? So there are instances when you can have only one stable matchings. That's easy. If let's say there are two people who are first choices for each other, obviously they will marry each other. But what's the maximum number that you can have? This is also important. There are different topics related to stable matchings like popular matchings, and we want to maximize some other welfare along with the matching being stable. So it's good to know how many options we have. For example, on how many things you have to go through to look for a certain matching. So any improvement on the number of stable matchings also improves the analysis of the running time of certain algorithms. Okay, a trivial upper bound for the number of stable matchings among n men and n women is n factorial, because you can have at most n factorial perfect matchings. Irving and Ladder proved that there's an exponential lower bound. Okay, an exponential lower bound is very trivial. It's very easy to construct something that grows exponentially, like 2 to the n, I think is still easy, but they could show that you can get something bigger, at least if n is a power of 2, but really it works for every n. For some reason, this was shown much later by Turber, that practically this lower bound holds for all n, up to some polynomial factors. Okay, but surprisingly, the upper bound wasn't improved for a long time. The best bound until recently was by Statopoulos, who proved an upper bound of n factorial improved by some constant to the n. So this is no big improvement, since the lower bound is only singly exponential in n. And then a breakthrough came a couple of years earlier when Karlin Garan-Weber proved that the maximum number of stable matching is singly exponential in n. But the bound was horrible. It was like 131,072 to the power of n. And of course, they noted that they didn't optimize, but yeah. Can anybody see what that number is? Just to make the talk more interactive? No? You should memorize more powers of 2, and then you will see. And we managed to improve this upper bound with my co-author to 3.55 to the n, which is quite close to the lower bound. Although if you plug in some small values, often you will see it's not that close, but at least it's in the same ballpark. Okay. Okay, so this is what I will tell you. And now I tell you our method for counting, how we achieve this result. So I won't talk about stable matchings now for a long time. So now I tell you our method. Any questions so far? Okay. So how do we count? Let's say that I have some S, a family of n tuples. You can imagine like from a grid, I pick some points. And I want to upper bound the size of S. You can imagine that the elements of S, yeah, they are ordered n tuples. A very trivial upper bound for S is, of course, the product of the cardinalities of the sets. Like imagine that S lives in a big rectangle or brick, then of course that's an upper bound. How can you do better? Well, for example, I could reveal the coordinates of S one by one. And if I'm lucky, then you will have less options for the second coordinate. Can you see this little hand on the screen? Good.
Yes, yes.
Okay, so for example, this XIS says that that will be the number of options for the I coordinate if the first J coordinates have been already revealed. So of course, we know that the first few coordinates are S1, S2, S3. Okay, so in this problem, I don't know S. I'm just revealing its coordinates one by one. And if I revealed I minus 1 coordinates, then how many options do you have for the I coordinate? You know, this might be less than the cardinality of AI, because the set S need not be a rectangle or a brick. So an easy upper bound for S is then we reveal the coordinates one by one. First the first coordinate, then we see how many options there are, we reveal the next coordinate, and of course you have to multiply these. And instead of going from 1 to n, you could go in any other permutation. This very fancy thing is just says that we go according to some other permutation. And of course, the same easy bound would hold. I need this for other permutations because then our trick will be to average over all possible permutations later. So let's see an example, because I know this notion is a bit confusing. Let's say that this is my S, okay, this L shape. So now n equals 2, we are just in a plane in a rectangle, and S lives in this rectangle. Of course, it has 2n minus 2 elements. You could count the little dots one by one. And the trivial upper bound would be n squared. That's the size of the rectangle. The easy bound is n times n minus 1. Why is that? Let's see. Of course, I said that this easy bound is the product of the maximum possible value of the xi at the point of revealing. So what happens first? Let's see it step by step. Let's say that the permutation is the identity permutation. So first I reveal the first coordinate and then the second. And how many options do you have for the first coordinate? You can have anything from 0 to n minus 1. So you have n options for the first coordinate of a point from S. You have n options for that. How many options do you have for the second coordinate? Well, it depends on what is your S, right? After I reveal the first coordinate, if I reveal the 1, a 2, or so on, so if I didn't reveal 0, then on that vertical line, you will have only 1 point. So that means that in this case, if you have one of the red points, then there will be only one option for the horizontal coordinate. We know it will be 0. If the first coordinate was positive, then the second coordinate will be 0. On the other hand, if the first coordinate was 0, it means that we have one of the green points. Then on that vertical line, you have many, many points. So in this case, you have n minus 1 options for the second coordinate. Okay. So this finishes the proof of the upper bound, because these are the two options. Either you have a red point or a green point. The worst case is if you have a green point. So this is how we get n times n minus 1. Okay, let me know if you have any questions so far. But I hope that the basic method is clear. And of course, I could have done the reverse permutation. Then first you reveal the second coordinate and then the first coordinate. Then of course, these things would be swapped. Then for the second coordinate, you always have n options because you reveal first the second coordinate in the reverse permutation. If you reveal the second coordinate first, you have n options for that. And then for the first coordinate, you have one option or n minus one options. But already here, you can see some trade-off. If you have a green point, then one is big, the other is small. And also if you have a red point, the other way around. Okay. So this easy band, of course, n times n minus 1 is not much better than n squared. Now I tell you a main lemma that we will use. This is this entropy type lemma. So in the first line, you just have the summary of our definition so far. And it says that to bound the size of S or the logarithm of it, you can take expectation over all S and then sum up the log of these xi's. So notice that this band doesn't depend on pi yet. This holds for any pi. I will briefly sketch the proof of this lemma for you later. Oh, no, I'm sketching it right now. Sorry. So I briefly sketch you the proof of this. Well, the first proof is that this is just like Shannon encoding. Those of you familiar with Shannon encoding, imagine that you must encode some text where the letters are drawn from an alphabet. The alphabet is S. So the size of the alphabet is S. And the letters come uniformly. Then, of course, you cannot encode the letter better than log S. That's the best that you can do letter-wise. You need, for every letter, about log S bits. And what's the other thing on the right-hand side? The right-hand side says that you get a random S, a random letter. You know that they come with the same distribution. And first you encode S1, then you describe S2, and so on. So instead of just telling what S is, first I tell its first coordinate, then the second coordinate. So I tell you as coordinate-wise. That's also a valid encoding. And of course, the optimal encoding, this is a theorem of Shannon, is that if you take, well, you can't beat the uniform. If the letters of S come, if all of them have the same probability, then you can't beat log S. That's an easy theorem. So I prove this lemma that I will use. And this is what I say it's entropy-like, because you can also prove it by entropy. This is another proof, again, a la Shannon, since he invented this Shannon entropy. Those of you who like numbers can also go through this entropy type proof instead of the more logical argument. But I won't go through the details. You can press the print screen button on your laptop and come back to it. Okay, another chance, last chance to print screen. Okay. Okay, so as I said, we proved the main lemma, but that's true for any pi. And now I will average. I can take the average for any probability distribution of the permutations. I just take the uniform distribution, but I could use any. And then I would guess that log S is always upper bounded by taking an extra average for the permutations. And now I do this trick that I swap these summation signs, and then I put the maximum over S here. Okay, so I took out this summation side outside. Here I keep the expectation over the permutation, and instead of taking expectation over S, I put here max. Why do I put max? I could leave an expectation there, but that's hard to control. A max is easier to bound. So I made my upper bound a little worse, but it will be easier to estimate it from above. Notice that if you don't like logarithms, it's a bit strange to take the expectation of logarithms, although it's there, for example, in the Alon Spencer book at one place. But so if you're not used to that, then instead of expectation of logarithm by Jensen's inequality, you could get this other formulation, but this is weaker. But keep it in mind that if it's hard for you to count expectation of logarithms, you can do this Jensen. All right, so this was our main lemma. Now let's see how to apply it. Remember our previous example that I started with? We already calculated this x1, x2, and so on. Now, I want to do the lemma. I just do Jensen because it's easy. So it says that the size of S will be at most the product of this max thing. Okay, how much is this max thing? Well, we do the product. Of course, I will do only one term. Let's say I do it for x1. It will be the same for x2. That's why I have a square, because this set is symmetric in the first and the second coordinate. For x1, what do I need to do? I take the S for which this expectation will be larger. I can tell you that it will be larger for the red points. You can see that x1 is usually larger for the red points. What will be x1's expectation for a red point? That means that I don't know whether I have the identity permutation or the reverse identity permutation. So I have to average over these two. The average of n and n minus 1 is n minus half. So this is what you get for x1. And you also get n minus half for x2. There the green points will give the maximum here. So that's how you get n minus half squared. I know what you're saying. This is not the best ever improvement I made in my life. In fact, this is even, I think, slightly worse than that. This is 1/4 more, but trust me, you can do better. For example, if I did the log of the expectations, then you would get something better, but still not too better. Oh yeah, I would just get back the easy bound with the logs. So I'm just showing you that if you do the log and not Jensen, then that's better. Well, you get 1/4 more. But anyhow, here, this method is useless. It doesn't give you any improvement at all over the easy bound. What I haven't done is that I didn't tell you that this S, I could have done it in 3 dimensions. Then you would again have a point set with 3 endpoints. Here, the trivial bound would be something like n cubed or n squared at most, the easy bound. And here, if you reveal the things in some order, then you would get a significant improvement. Let's do the x1 coordinate. For example, if you want to do the x1 coordinate, then it will be the largest for this type of point or the bottom type of, oh no, this. Yeah, the first and the second will give the worst. So if you want to average the logs, let's say you can take this point to get the max of x1. And I have a 3 here because I have x1, x2, x3. These are all symmetric. I have a 1/6 because here I have 6 permutations. And let's see, I have 2 permutations where the value is n. So I have log n. I have 1 permutation where it's log n minus 1. I have 1 where it's log 2 and 2 where it's log 1, which is anyhow 0. But if you look at this, then you can see that it's about like log n cubed, but you have this 1/6. So, oh yeah, half. You have log n cubed here, and this gives a half. So it will be n on the 3 on the 2 power. Okay, so here you really get an improvement. And of course, this is also, you will get much better improvement for stable matchings. Just I wanted you to get the method. Okay. Any questions? Good. Now I tell you Bregmann's theorem. I'm sure that many of you heard of it. It says that the number of perfect matchings in a bipartite graph is at most the product of di factorial on the 1/di. The di denotes the degree of vertex vi in one part. So it's important that I multiply only the degrees of one side of the bipartite graph. You can pick which side. It holds for both. And it might give a different number, I think. Okay, so there's a nice proof by Radhakrishnan with entropies. And instead of entropies, I will use our main lemma. Let's see how. S, a collection of sets, will be the perfect matchings. Of course, that's what we have an upper bound. The set AI will be the edges incident to a VI. So I encode the perfect matchings by telling for each vertex VI which edge is adjacent to it. Okay, that's how I'm encoding a perfect matching. So let's fix a matching and let's order the vertices in V according to a random permutation. And then what will I do? I'm telling you, A1, A2, and so on. So practically, I'm revealing the edges of the matching one by one. First, I reveal the edge incident to V pi 1, then the edge incident to V pi 2, and so on. So xi s pi is the number of options remaining for an edge incident to Vi before revealed. So I'm about to reveal the match, the edge adjacent, the edge incident to Vi in the perfect matching. Already I revealed I-1 edges, let's say. or maybe I revealed more. If pi is not the identity, then you don't know how many edges before have been revealed. Let's denote by ni as pi the number of neighbors of vi that have not yet had their edge from S revealed. Vi will be matched to one of them, right? Because those vertices that are adjacent to Vi, but their edge from the matching is already revealed, of course, Vi cannot be revealed to them. I mean, Vi cannot be matched to them. So Vi must be matched to somebody from Ni. So in particular, this means that Xi will be at most Ni. Note that Xi might be smaller because it's possible that Vi has an unmatched neighbor, but it cannot be matched to Vi in a perfect matching, extending the edges that have been revealed so far. But at least Ni is an upper bound for Xi. Okay, and the nice trick that Radhakrishna noticed that what's the probability that Ni equals K? Well, it's just 1 over Di for every K. It just depends on how the S has Di neighbors, and it just depends on when the vertices matched to those neighbors are revealed in pi. And that's a uniform random probability distribution. So the chance that Ni equals K, we know it exactly, it's exactly 1 over Di. And from here, the rest is very easy. I can just plug in my formula. Log S was the maximum of this expectation. Xi I can replace by Ni because Ni is always larger. And this I can calculate now because it doesn't even depend on S. That's why I could put a max there. It doesn't matter at all. I will take a sum over all possible values of Ni. I know that each of them has 1 over Di chance. And of course, it's a number running from 1 to Di. So I have to calculate this thing. And that's exactly what we wanted. Okay. So this was a step-by-step retelling of the proof of Radhakrishnan, just he did all this with entropy. I didn't see entropy even once. I only used the lemma. Any questions? Okay, well, if you won't remember anything from my talk, at least you heard this very nice proof by Radhakrishnan. Okay, let's go back to stable matchings in case somebody has forgotten. We have a complete bipartite graph. We have a preference list, men have over women and women over the man. And we have these blocking edges that we don't like. So the preferences that give many stable matchings, they look something like this. I tell you what this is. Here are the men, those are the women. And on the left, you always have the ranking of that woman on the men's list. And on the right, you have the ranking of that man on the woman's list. So in every stable matching, this is by Gale and Shapley, there's a so-called man optimal stable matching, where every man gets the best partner they can get in a stable matching. In this case, they even get their first choice, but it's not always the first choice. But there's always a man optimal stable matching where every man gets the best possible woman they can get in a stable matching. And this is another stable matching, which is a little better for the women, yet another stable matching. Notice that I always swap some pairs and it keeps on getting worse for men and better for women, and then finally reach a woman optimal stable matching. So these stable matchings, they have a nice structure, and it was observed by Irving and Leder that every time you make a change, you have a certain rotation. Like, for example, in this example, I kept on swapping pairs. It might not be swapping pairs. It might be swapping a longer cycle in a rotation. Just in this example, I did only these cycles of 4, but you can have a cycle of 6 that you change. And we say that the rotation is exposed if in the matching, it's half of its edges are there, and the other half you can swap to. And sometimes you have unexposed rotations. For example, if you start from a man optimal stable matching, then obviously you cannot do this rotation. That's a C4 because its edges are not there. And they prove that the rotations form a nice poset. And beware that if you heard of stable matchings, most likely you heard of the poset of stable matchings. This is a different poset. It's not the same. The poset of rotations is a different poset. Okay. But these rotations always also have a poset, which tells in which order you can execute the rotations. And the dance sets in this poset are in one-to-one correspondence with the stable matchings. This was also proved by Irving and Leder a long time ago. Just let me show you how it is. For example, I will always display here the actual stable matching. Let's start from the man optimal. And then if you execute one rotation, let's say the left one, now there are two rotations that are exposed. I can either do this rotation next or that rotation to get another stable matching. Now I again have two choices to do something. Here again, I have two options. Now I only have one option, sorry. Also before. Yeah, I can do this rotation. I only have one option. Now I have to do this rotation next. Now I have two options. Now again, I have only one option. Anyhow, this poset can look more complex, of course. I'm just giving you a simple example. You keep on doing rotations, and you can see, for example, this dance set is matched to the stable matching that you get after you execute these rotations. So this was the one-to-one correspondence, but you don't need to know the proof or more about it. What Carlin and Garan-Weber noticed was that the rotations that involve a fixed person form a chain. So what is a fixed person? It can be any man and woman. For example, if the fixed person is M1, then I highlighted those rotations whose top row is not empty. That means that the first man participates in a rotation. Or a fixed person can be M4, the bottom row. Or it can be a woman. The columns correspond to women. So here the last but one column will correspond to the rotations that involve the third woman. And notice that the chains of a man and the woman are paired twice if they can be matched. So that means that one of them had a child, no. So that both of them have a chain, and that chains might meet several times, but there's one rotation here when the top row and the third column where they are matched, and another place where they are unmatched. So there's a rotation where we say that, okay, from now on they are together, and the next rotation that involves them will make them split. Okay. And everybody can be matched to each other only once, because remember, the situation of man keeps on getting worse, and the situation of women keeps on getting better as we go upwards with the rotations. Again, a picture of the whole thing. Imagine that the red is the chain of M1 and the green is the chain of M3. And these chains might meet several times, but there's only one place where they are paired in the rotation. And also notice that this is not a graded poset, so it can happen that somebody has more rotations, somebody has less rotations. The important thing is that every man and woman can be paired at most twice, even though their chains can intersect several times. Again, I'm depicting the same thing again. Let's say that you have the jade woman on a chain. Initially, in the man optimal matching, maybe she is mapped to M1. Then at this rotation, she would be unmatched from M1 and matched to M2. Then she would be unpaired from M2 and matched to M3. These two lines are the same thing. I just put them at different heights to make you see what's going on. Okay. So this structure shows that this is very simple, right? We like it a lot, because whenever you take a woman and her chain, then the structure is very simple on it. You don't know which men are there on her chain, but you know that they follow each other in a super simple pattern. And we will be able to exploit this symmetry to apply our method, which works well for these symmetric things after we do some permutations. Okay, so what's our new goal? Now we can forget about stable matchings. We want to count dance sets in a poset that we call the two-tangled grid. What is a two-tangled grid? So it's a poset such that it has a greatest and the least element. This is like the man optimal and the woman optimal matchings. It has two n-member families of chains. Every man had a chain and every woman had a chain. And we know that for every element of the poset, which corresponds to a rotation, there are the same number of M chains and W chains in it that will swap there, that are paired to each other there. Okay, and we know that at the man optimal and the woman optimal, everybody has a match. These are a bit special elements, the top and the bottom. There's a complete pairing there, and at every other element, there are two pairings of the man chains and the W chains that contain that P. There are those, everybody is unpaired from someone, and everybody is paired to someone. Okay, so every M chain that contains P has two W chains paired to it. And we additionally know that in every W chain, we have a nice structure. Every man chain can be paired to it twice, and that those two occasions are at consecutive parts of the W chain. And for every M chain, of course, we have the similar thing. Okay. Good. Now, how will we describe a dance set in such a two-tangled grid? We will randomly order the M chains and the W chains, and I'll describe the dance set by revealing the largest element on every chain. So if on every chain I tell you what's the largest element, you will of course know the largest element because these chains cover the poset. In fact, this is a redundant way of encoding. It would be enough to reveal the largest element only on the man chains, for example, because those already cover the poset. But we also need to reveal it on the W chains because that will help us. So this redundancy helps. And then what is the expected number of options for, let's say, the top element on a W chain? Now we will exploit that if we revealed some M chains before this W chain, then we will know whether their intersection is in the dance set or not. And remember, this W chain will have many M chains intersecting it, well, exactly as many M chains as long it is. So for example, here is this W0 chain. It has all these M chains on it. Let's say I know that 2 will be revealed before 0. So M2 is revealed before W0. Maybe I should have used a different pi for 2 and 0. Anyhow, men and women, I'm using the same pi. Then let's say that I know that this element of M2, I know about all elements of M2, whether they are in the dance set or not, because I know the top element on M2. Let's say I know that they are on the dance set, in the dance set, then all these elements of W0 are in the dance set. Let's say that next 7 is revealed. I will know that all these elements, let's say they are not in the dance set. I will know that all these are not in the dance set for W0. Let's say next I reveal 3, then I know that all these are in the dance set. If now W0 is revealed, then you will have only 3 options for the top element of the dance set, right? 1, 2, 3. So this is my way of encoding. And this is why if many chains from the opposite sex have been revealed before a chain needs to be revealed, you will have likely few options. Okay, so what is the expected value of this log x for a given chain W0? Well, to solve it, there's a very nice puzzle. And now is a very good time that if you haven't paid any attention at all so far, to pay a little attention, because this is a really puzzle, and I'll give you some time to solve it. So let's suppose that there's a circle, and it has a fixed red point. Then I randomly pick 10 black points on the circle. Every black point is picked uniformly, independently, somewhere along the circle. Now my question is, what is the expected length of the arc that contains this red point? I give you some time, and feel free to guess any number. This is a puzzle not related to anything I told you so far.
Every interval between 2 black points should have expected the same length, right?
So it should be,
well, 10 points, 10 intervals, 1/10 times what?
So you're getting 2/10
Mhm.
or 1/10 because there are 10 black points.
Yes.
Now you see the problem with this logic is that the red point has a higher chance of falling in a long interval and a smaller chance of falling in a short interval.
That's true.
So your answer should be more than 1/10.
That's true.
I had a very complicated proof for this, but then my wife told me a super simple proof. That's the solution of this puzzle. Any other guesses?
Shouldn't it be that the red one should be also considered to taken at random? Then and then all you do is you take 2 intervals on the. I'm missing a word on the circle.
Something like that.
And
Meanwhile,
then, yeah, so this should be 2/11 then.
very good. Meanwhile, in the chat, we also had a correct solution by Pat Morin.
Oh, Pat. Okay.
Exactly, it's 2/11. Very nice. Then you deserve the rest of the talk. Maybe you would deserve me stopping at this point and not going on with the talk. But
can I turn off the camera?
Okay. So, right, can I click back here? Oh, yeah, this is the proof. So why is it this? Because imagine that you pick 11 random points and then you pick which one is red later. Then of course this is the same probability distribution, and then for every arc to be selected, you have 2 ways for it. Okay, so you have 11 arcs. On the average, they have 1/11 length. You pick 2 of them, so it's like 2/11. You said a similar logic, I'm sure, why you said 2/11. Okay, so this is a nice puzzle, and this is what we need exactly, because this is what we have, right? What we have here, instead of a chain, imagine that I had that chain, the woman chain, and on it I have some man chain that appear on it somewhere. Well, we don't know which man chain appear. They appear somewhere uniformly at random. So imagine that this long thing is the chain of a woman. The red point is the topmost point of the down set. I know we have an interval and not a circle, but it doesn't make a big difference. And somehow you have some men that appear that were revealed before the woman. Those correspond to the black points. And then the length of this arc is the remaining number of options for the red point, because in real, I don't know the red point. The red point is the topmost element of the down set on my chain. What I have is only these black points, and I know between which 2 I will have the solution. Okay. So what we have here is, of course, to bound the number of S. Now I'm only using this weak bound for Jensen, where you take the product of the expectations. It doesn't matter whether you take men or women, so I just put a square here, and let's do it for just woman chain for simplicity. Then I have that, what's that probability that I man chain were revealed before it? Well, the probability for every that for I were revealed before it is 1/n for every possible value of I. And if I were revealed before it, then I know that the answer will be 2/i+1 for the puzzle, but 2/i+1, I need to multiply it with the length of the circle. The circle is not of length 1. The circle can be at length n+1. The woman chain might be n+1 long. So that's why instead of 2/i+1, I have an n+1 factor here. And of course, I have this 1/n that comes from here there. So this is exactly how we calculate this expected value. And you have some small things where you have only, and when that woman chain is the first or the second or something like that. And you must raise this to the 2n power. And if you look at the formula for this summation, then of course it's something like log n. And then you get something like 2 to the n times log n. Well, this is not better than the result of Carlin and Garantable, but it's already better than the n factorial bond that was known before. And this was the weakest bond that you get from Jensen. I just did this because here I can give you all the details and you can understand the proof. Because, of course, in real we have a harder puzzle. If you want to get a better bond, given a fixed red point and some random black points, what is the log of the expected length of the eye containing the red point? Here, I don't have a nice solution. And in fact, the log doesn't even make sense. Or, I mean, it depends on how many points you have distributed on the circle. So the answer should depend on that. So you can do this ugly summation. And in fact, that ugly summation has a nice formula. So there is a combinatorial way to simplify this, but the best is just to assume that n tends to infinity, and then you can reduce it to some integral. So you get something like this. I'm not giving you all the details, it's just some calculation. And then for the log of S, you have some other bond, because of course we have to do is 2n times, because there are 2n chains. And from this, you get that S is at most 11 on the 11 to the nth power, which is already much better than the previous bond. So this already beats that 2 to the 17th to the nth earlier upper bond. Okay, but I promised you something even better. So I will bore you a little with the details. How can you get an even better bond? Well, let's suppose that the Dahn set is that on the W chain. Then there is an M chain that if that is revealed before W, then you also know the top element on W. Of course, it's easy to see that that will be M4. If M4 happens to come before W0, then you can see that on M4, one of the elements is in the Dahn set, the other is not in the Dahn set. And those are just two consecutive elements also on W0. So if you are that lucky that exactly that M chain is revealed before W0, then you have nothing to do at all. Of course, I mean this M4, that depends on the top element of the Dahn set, but for every top element, there is such an M4. But if M4 comes before W0, then we know that the number of options, X, will be 1, so its log will be 0. So then we don't have to do anything. And what's the chance of M4 coming before W0? 50%, right? Because I took a completely uniform permutation. Then you can redo this calculation, which will be slightly better. Now it will be 6 on the power of n. Notice that you didn't get it halved, because again, if m comes before w, then that's very good. I have nothing to do. But if m comes after w, then most likely other things also come after w, right? These are not independent events. If m came after w, then most likely other m chains also will come after w in a random permutation. That's why we don't get the half of 11, but just something like 6 instead. And you can do even better if you even look at the W chains. Remember, I said that at every rotation, you have at least 2 M chains and at least 2 W chains featured. So if you happen to have this W chain somewhere, sometime it's revealed, this WP, again, I don't know when it's revealed, but sometimes it is revealed, then you get a lot of information. If, for example, you're that lucky that P and Q both happen to come before W0, then again, I know the top element on W0. These are just some other W chains that are featured at these very rotations. And of course, if only one of them comes, even then we can gain some information. And then also you can look at the element before them. Here I could take someone who's not WP, but is featured at this rotation. Know that it might be WQ. And then I can also look at that. So we went this far and we calculated all the probabilities. The worst case is when all these 4 W chains are all different. And then we got a very, very ugly formula, but we had some math software to help us with the calculations, and that spat out 3.55 to the end. Okay. Any questions? Anybody spots any mistakes in the integral or summation? Okay, and after all these ugly calculations, I left a last trick to the end, because now I only proved 3.55 to the end plus some constant, which is not so nice. that comes, you know, because I switched to integrals and I said that the first term, so there were some unpleasant things. But I can take it down to 3.55 to the n. And this was not there in the Fox paper because this last trick I only learned in September from Peter Pálvölgyi, who gave a mini course, and I attended it. It was about something completely different, but he just used the trick, which is also exactly what we need here. So the very nice thing that if you know that the number of stable matchings is at least c to the n for any c and any n, then I know that this number of stable matchings for t times n is at least c on the t times n power. This is just simply because you have a copy with n men and n women showing that you can have many stable matchings, and you can put t copies of this construction such that everybody in this copy prefers everyone in the same copy to those people in another copy. Okay, if you do this, then of course you can have a stable matching here and a stable matching here, and they won't interfere. So that's exactly how this gets multiplied. So if you have a stable matching like this, then you also get one there. But this implies that if you have an upper bound of 3.55 to the n, then that holds for every n universally. Because even there's a single n violating that condition, then you could use this thing and show that it also gets violated for some large n. So this is a very nice trick, and really, they didn't know it. So the Fox paper appeared with this slightly worse bound. And also none of the reviewers noted that you could do this nice simplification. But this finishes the story of our result. So thank you for your attention.
Thank you, Dömötör.